Okay, a couple things I want to review with you before we get to the quantum theory of hydrogen and make our first approach to the periodic table, which we'll try to get done today. I want to mention that SI this afternoon, as usual, 2 p.m., 4:30 p.m., as always. And there's a grand review to get ready for the final. Apparently, SARC has a page with all the different ones, chemistry and biochemistry and so forth. This is the one for physical science. Here's a blow up. So that'll be next Monday, 2:30 and 4:30. Now, you guys go next Thursday, right? For your final, 7 a.m. So anyways, this will be good, 2 hours. And as I have mentioned before, if you can only catch the last 30 minutes or the first, 45 minutes or whatever it happens to be, you go over there and get some reinforcement. It's definitely going to be helpful for you. The SI students usually do a full letter grade larger. Okay. And in general, the study union over in the student union, here's the website for it if you want to jot it down. They have a bunch of other stuff. They have SARC review sessions for SI. They have a bunch of other stuff. And you newbie freshmen, you may not feel like newbies anymore than now that you've been here for a couple months. But definitely keep this in mind that, there's all kinds of stuff that can help you increase your grades on finals. Because we got to, you could still biff it. You can still mess up your grade if you're not careful. And the final exam is a big chunk of dinero. So you don't want to mess up on that. For you newbies, my main bit of advice to you is get sleep during finals week, or you will pay with bad grades. And you sometimes see me on exam days coming up here to class, and I look like I'm frazzled beyond, a fare thee well, because a lot of times bringing 2 cups of coffee. Is one of those for me? No? Gosh. Dunkin' Donuts. A lot of times I come here on exam days, and you guys see me first. And a lot of times, I work my what off to get the exams ready for 9 o'clock. But sleep is your number one weapon, simply because if you don't have sleep, you may think, I'll do an all-nighter. That's what you do in college and stuff. Yeah, if you want to have stinky grades, that's what you do. But plan your time. Also, program your cell phone with 2 or 3 alarms just for safety, because, especially for you guys on Thursday, do not be late for the final. It's 7 a.m. And if you're not here before the first person finishes, that is it. You cannot take the test. You've got to be here on time. Okay, so this business of, the dog ate my alarm clock or something like that, that's charming and lovely and nice and humorous. But on exam day, I'm going to say tough toenails, on that. You just got to be here. So sleep, just like this hound dog here. All right. A couple things I want to go over with you about updates in your grades page. And just before I do anything else with that, let me just mention that the grades page is there. I'm still working on it. I put some stuff up this morning, like total points, but I apparently forgot to upload your exam 3 scores. Although you can deduce your exam 3 score, your part 1 score and your total from the numbers that are up there. But I'll be getting that up this afternoon and stuff. Anyway, I've computed for everybody really carefully, best 2 out of 3 midterms. And you know, there's a huge number of you that were here for all 3 midterms. And so, but there's a few, I think about 20, 30, so maybe about 10% of this and the other class that weren't here for one of the exams. Now, if you only had 2 exams, then those are your best 2. If you were absent for exam 1, exam 2, or exam 3, then those are, then you only have 2 exams on the books, and those are your best 2. So I made a Alondra, is that exam code visible, Brittany? Is it? Okay, so there's a row of your grades page that has exam code on it. And what that means is simply a number, a pair of numerals to tell you which exams, went into your best 2 out of 3. Now, if you have all 3 exams on the books, your code is 1, 2, 3. All right, because you got exam 1, you got exam 2, you got exam 3. But if you missed exam 3, then you have a code of 1, 2. If you missed exam 2, then you have a code of 1, 3. And if you missed exam 1, then you have a code of 2, 3. So hopefully, and that's just a few of yous, you should be able to figure it out. All right. Another thing, homework converted to 25 points. But we're not done with that, because we're going to have some more homework this week. And we're going to have a big ginormous, we're going to have, we're not going to, I hate to say this, we're not going to have homework tonight. I know that's going to cause a lot of mental anguish. But you will have you'll have regular homework Thursday night, and you'll have a big mega review homework that I'll convert to bonus points, as I've mentioned before. That'll be going this weekend. Also, Chapter 7 mini review, I cannot download it yet from the Great River website, but I will, and when I do, I'll get that in there. Oh, by the way, the Chapter 6 fiasco review, I basically just added 4 points to everybody's grade. Unless you had 10 out of 12, then I added 2 points. So everybody's got the full, those two problems that were blooped up. Now, the thing about it is, and I want you to listen carefully, the Chapter 6 mini review number that's in there right now doesn't reflect those 2 or 4 more points that you get. In my spreadsheet here on my MacBook, it's in there. The total points reflects that. All right? So the total points that I uploaded this morning, about 6 o'clock, 5:30, 6 o'clock, for your viewing pleasure, that's got the homework 6 squared away value in it. All right, now I'll get to the Chapter 6. I'll get that updated sometime today. I got a lot of updating to do in your guys' grades. Question? Call it.
Do the total points reflect the 15 bonus points from iClicker participation?
15 bonus points? 15 bonus points? You wish.
Yeah.
No, it's 4 bonus points if you get it. And no, they do not, because I haven't awarded them yet. Okay, so it does reflect anything you got in the early iClicker registration. And then after, this coming weekend, I'll figure the clicking bonus. All right. Let's talk about that, clicking. Here are the specs. 85% leeway factor is 57 answers or more. And a huge ton of you. You know what else I looked at? I put together a column in my spreadsheet for everybody, their homework and their clicking participation together, kind of a combo grade. And you guys did really good. There's a lot of 47s, 48s, 49s, and a whole bunch of 50s. And that's like a midterm. So, yeah, we're doing good. All right. The roundup figure is dated 11/15, and that's the most recent clicking that we had up till today. So and one more thing, let me just add this in. I'm not going to do any more grade updates until after the final. Okay? And so your grade is not going to change a whole lot between now and the end of the week. And we got a little bit of homework, but you're going to have some bonus pointage. So if you're near the borderline between C and B, B and A, F and D, some people are trying to scrape by and get a passing grade. That can change with bonus pointage, but that won't go on. Usually, just as a public service announcement, I'll just tell you, Diamond, and everybody, that I don't normally put all the bonus points on until after everything else is done. So that means after the final. So if you come up to me and say, Dr. B, where are those 15 bonus points? I'll say, first of all, no, there's no 15 bonus points, you wish. And then I'll say, I usually don't get to those till after the final. So, but I'll try to get them done this weekend. I sometimes get some work done on that. All right. And right now, the total points, this is righteous. This number, everybody can see, and it is fairly accurate. Except two students that I don't think are here, but that's pretty accurate. Now, I want to go through what it looks like in the grade book. And so you have, some number, like 133 out of 150 for your total points. That is good. You have homework points as of 11/20. So that was the last homework was due on the 20th, the exam day. So that's the as of date for that. And participation pointage as of 11/15. Now that should be near the top of your grades page. Okay, so there's going to be a lot of 24s and 25s and 23s and stuff like that for most of you. Okay, then below that is the early iClicker stuff, which you've already seen. All right, so take a look at that stuff. Now, down below the early iClicker, you'll see your sum of all your homework scores. Now, that's out of 308. All right, so for this imaginary student, I just put in 294, and 294 gives the student 24 out of 25, percentage-wise. And don't forget, I always round up when doing this. All right, so here's your homework scores, and yeah, that's down there. Oh, by the way, I set up grades and assignments so that if you click on arrange by assignment type, I think it is, you'll see everything fairly well organized. If you go by due date, it'll look like, all discombobulated. I mean, all the data will be in there, it just won't be sorted the way that I mean it to be sorted. So the way that you're looking at it right now. Okay, a little bit further down, underneath the homework, best two midterms, and then your exam code, which I already talked about. And so basically, I just add up all your if you add all three, then I add them all up, and then I subtract the smallest. And it's pretty easy to do in a spreadsheet. Question?
So are you doing, when you do like the exam, like for the exam ones, you're doing like the exam total, like plus the figures and the...
Yeah, this figure here, total points, oops.
Like where it says like exam 2 total, like that's what you're using?
Yeah, exam 2 total is what I go, that's your exam 2 total.
So I just want to know, how can we, you are exam 3 and it's not confusing. Like how can we pick?
Oh, good. Brittany, You were supposed to ask me about that. Exam 3 grades. I forgot to upload exam 3, part 1, the clicking and the total. They're in, so that's what you're asking about, right? Yeah, how can I do it? I have it, but I forgot, I uploaded the other stuff, but I forgot to upload those 2 columns. But I'll be doing that today, so. All right, and that'll go into total points right up here. And I believe actually this is the very top thing in your grades page at the very top. If you view by assignment type. Okay, best 2 midterms and exam code. We already talked about that. And 123 is the code that you have if you've been here for all 3, which is most of you. Question? No question? Okay. So now, the roundup figure is right here. All right, now it's something points, it's out of 66 questions. All right. So this particular example, the student has 51 questions answered, and 43 of them are correct. And as Khalid was asking, the 4 bonus points comes out of how many correct you have. If you have 75% by the end of the semester, then you'll have 4 bonus points. But we're not ready to do that yet, so... but hopefully this weekend we'll be able to do that. Now I want to draw your attention to something with a puke green outline. And I know some of you have asked me, hey, Dr. B, why don't we have the totals down there? General data, bonus point activity, homework and stuff. And the answer to that is I never activate those numbers. I always deactivate them because they lead to trouble. Web Courses Canvas cannot handle our grading scheme, and I've got something important to tell you about your grades in a second here. And if I was to grade the way Web Courses grades, you guys would be SOL. But basically that stuff down there at the bottom, I just deactivate it. So just think, no. Dr. B is not going to ever activate those numbers. But I don't think I can completely turn them off. I think there's ways like in your dashboard or something that you can still see some percentages, but I turn them off as much as I can. Now, here's what I want to show you. You're right now, the points basis for everybody is 150 points. All right? We're assuming that everybody's got 2 exams on the books, and that makes it 150 points. Total possible regular points, not bonus points. All right? And for that reason, the grading scale looks like this. Okay, so if you have 135 points or more, right now, that means you're going into the final with an A. And right now, my wonderful students, in the 2 lecture sections, there are 60 students with A's. There are students that last week were saying, Dr. B, I'm so nervous about my grade. Please help me. And they have a B. Matter of fact, there's 189 students with a B. And 77 with a C. And look at that. A D, there's a few students. But we've got almost 400 students in the 2 sections. 14 out of 400, that ain't bad, my friend. 6 out of 400, that ain't bad. And this, girls, please, I can hear you all the way up here, and you're distracting me. I should have your full attention, all right? Because you want to know about your grades, right? Right? Yeah, that's. Now this grades, the numbers over here in the right-hand column are lovely and totally unexpected. This is my patented grading system because now all your clicking and all your homework, your faithful homework activity is coming home. A nice chunk of change, 47 out of 50 for a lot of you, 48 out of 50, 49 out of 50, and for a whole bunch of you, 50 out of 50. And that's like acing a midterm. By the way, somebody crushed the midterm. I don't know if it's a student in here. They got 54 out of 50. I'm gonna have to start making harder tests, I guess. But no, I'm just kidding. I always say that. But I'm happy to see you guys crush. And you know what else this tells me? You guys are starting to crush things. I mean, you may not feel like it, but there's a lot of you. You're going to look at your totals as of 11/20, and you're going to say, "Hey, what the? I got a B in here. Ooh, I've got a C. I'm okay. I'm not going to flunk." All right? Or you've got an A and you didn't think, "What? How did I get an A?" And some of you I already told, you got an A coming in, so. But I was sending out some messages last night, and I told my wife, this is one of the fun parts of the semester for me. When I could tell a student that asked me about the grade and they're sweating it out, and I said, "No, you got a B, you got an A." I love doing that, and it's going to be true for a whole bunch of you. All right, now not everybody, but a bunch of you are doing pretty good. So now, if you want to talk over the specifics of your grade, I do not want to do it in messages in Canvas. All right, but if you come to office hours, or if you track me down like Chinatown, wherever I happen to be on campus, I'll just say, "Yeah, okay, let me look at my spreadsheet," because I always have my computer with me on campus, and so I can always look at your grades and stuff and say, "Oh yeah, okay, here's what you got," and blah blah blah. All right, so Tiffany, everything's looking good. All right, and we're just going to keep going. Now, I want to warm up your brains with a clicker question, so get your clicker ready. Everybody's here now, so let's do a little clickotaceous concepts. And this will be question 67 for the semester. Which formula for gravitational potential energy, GPE, holds near the surface of the Earth? Go ahead and vote. And I should say, and only near the surface of the Earth. Wait a minute. You know what? I'm going to do something. I'm going to ask this again. Hold on. Type in A or B and then hit the send button. And this way I can grade it appropriately. Do it again. Type in your answer and hit the send button. Get a check mark, please. By the way, you guys are the genius section. Sweet. Yeah, the other guys, they're okay. They're pretty smart over there, but in the 1030, but you guys, it's obvious. And I take my hat off to everybody here because I know most of you guys are really working hard. Even though you try to pretend that you're not. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. And you know what? Actually, both of these are correct. So that's why I changed it to short answer so I can grade it, both of them correct. The one up on top, A, is the general formula for gravitational potential energy near the surface of, near Earth or anywhere near Earth. But if you're just in the first, 40 kilometers from the bottom of the ocean to the top of Mount Everest, right in there, B is highly righteous. And we've studied that before. That's what I want to talk about. Gravitational potential energy, and most of all, electrical or electrostatic potential energy. All right, now, we just talked about this one. Good old GPE minus MGY. And here's the one, it's a little bit fancier. The distance dependence is actually in the denominator. And you may be thinking to yourself, Dr. B, how does it go from distance dependence in the numerator to a distance dependence in the denominator? And the answer to that, my wonderful students, is calculus, which I will not. If you were engineering students, I'd go into it. But it's, if engineering students can handle it, we'll let them take care of the light work. We'll do the heavy lifting. We'll do the concepts and stuff in this class. All right, but that's true for gravitational potential energy between the Earth, capital M with a subscript of a circle with a plus sign in it. That's the astronomical symbol for Earth, astronomers use. And then M, little m, lowercase m, stands for the mass of the satellite or whatever spacecraft you've got in orbit. Or the baseball, it works for it works on terrestrial scales as well. It's just that this one up here is much easier on terrestrial scales. Now, electrostatic potential energy looks very similar. And what I'm going to show you is the electrostatic potential energy for a hydrogen atom. So here it is. Okay, hydrogen atom, a proton, and an electron. Okay, there's the proton in the numerator. Charge E. And then here's the electron, also in the numerator, charge minus E. Okay? And then, of course, Coulomb's constant, K. And then the distance between the center of the proton and the electron, that's in there too. Okay, that's R. All right? So they look very similar. All right? And here it is, just kind of made a little more compact. All right? K minus K times E squared over R. And that's the one that we're going to be studying today. And we're going to be studying it in the context of the hydrogen atom. And we could study it in the context of the Van de Graaff generator or any other electrical system. But for us, we're trying to get to the periodic table and get a handle on it. And the very simplest element in the periodic table is hydrogen. So we're going to apply this today and think about this in terms of hydrogen. Now, side note, last week, or actually 2 weeks ago, we talked about the electric field lines. They point away from a positively charged object like porcupine quills, and they point inward towards a negatively charged object. And for an electric dipole, they have the kind of curved but still symmetric arrangement, the field lines. The electric field has units of newtons per coulomb. Excuse me. Oh my goodness. I just blazed up my... Doggone it. I just broke my big head. I just broke this. Nice. Just because I sneezed. I don't know what I'm going to do with this. Well, let's see if we can still use it. I feel another sneeze coming too. I'll break the others. Oh, Lord. Anyway, so now you may have heard this concept of voltage. You know, like 120 volts, household current, etc., etc. Now, a volt is analogous to electrical potential energy. And it's basically, the amount of joules per coulomb. Electrical potential energy, you can measure it in joules, like any other energy unit. Okay? So a joule is the same as a coulomb times a volt. C times V. Coulomb times a volt is a joule. All right? That's in the metric system. Now, in atomic systems, it's better for us to use the charge on the electron, the fundamental charge E. And so the fundamental charge E times a volt is an energy unit. It's called the electron volt, the EV. Okay, and that is an energy unit. And so in atomic and molecular systems that we're now going to be working on, the unit of energy is going to be electron volts. We're not going to do any joules. I mean, you can, I'll probably give you, like Planck's constant, you can give it in joule seconds or electron volt seconds. Okay? It's most convenient to use Planck's constant in EV seconds. All right. Now, I want to pause the... I can't believe it. This thing is completely... Big head. It's completely broken. We're going to do a demonstration up here, and I need 2 volunteers from the audience to come help me with distributing some equipment. Come on up. Come on up. Up to the stage. It'll just take a second. We're going to do a demonstration of the discrete spectrum of hydrogen. And this demonstration... All right, so this is the discrete spectrum of hydrogen, helium, and neon. And this photograph here is actually from the big lecture hall over in the Mathematical Sciences building where we sometimes teach this class. Now, here's hydrogen. That red hydrogen line is known as H alpha. Now, if we were in the laboratory, we had a good flat, instead of being up on the stage here, and we have, a table and everything is on the same elevation, and we measure distances and stuff and do a little bit of trig, we can figure out the wavelength of each color. And for H alpha, the color is 656 nanometers. Now, and as you guys know, once you know the wavelength, you can figure out the frequency, right? Matter of fact, the frequency is actually very important for the energy. So here's a little table. The brightest color, and this one was H alpha close to the central image or farthest away from the central image? Is farthest away. It bends the most. It diffracts the most. So 656, 457 terahertz. Remember we did that calculation? 457 terahertz a couple weeks ago. Okay, the next one is called H beta. And when we look out in the universe, Connor, we'll see a lot of stars with the H, that kind of turquoise-ish line. And sometimes if the temperature is right, if the star is really hot, we'll see more of the turquoise H beta than H alpha. The first of the purpley blue is H gamma, 434 nanometers, and it's about 691 terahertz. And then even deeper in the purpley blues is H delta. And H delta is 410 nanometers wavelength, so about 732 terahertz. And so for us, there's a question. Why isn't the hydrogen atom, this tube of pure hydrogen, why doesn't it give us the same spectrum as a hot light bulb? The first one that we looked at, the thermal source, the incandescent source. Why isn't it continuous? Why don't we get a rainbow? Why only these four colors in the visible band? Do you know what else? There's some infrared and there's some ultraviolet produced by hydrogen as well. We can't see that, but these ones we definitely can see. So the question is, there's a certain set and no others. Does it form a pattern? There's your question in boldface and underlined. Does it form a pattern? In other words, does it go by wavelength? Does it go by frequency? Does it double with the wavelength? Does it double with the frequency? And it turns out that the pattern in hydrogen is very, very tricky. Now, there's a guy in Switzerland that figured it out, named Balmer. Here's the pattern. And this is called the Balmer formula. 1 over the wavelength is equal to a constant, capital R, called the Rydberg, which I'll give you in a second, times the quantity, 1 over 2 squared minus 1 over n squared. And each color has its own value of n. So H alpha, n equals 3. H beta, n equals 4. H gamma, n equals 5. H delta, n equals 6. So the question is, the guy that figured this out, his name is Joseph Balmer. And I have no idea. He must have done a lot of scratch paper to figure this out. Because first of all, it's 1 over lambda, and then there's these squares of the numbers, and it's just integers, and it's very tricky, but it actually shows some underlying theory. Now, R is called the Rydberg constant, and it's equal to 1.097 times 10 to the 7 inverse meters to the minus 1. Right? That goes over here. Boy, this thing's digging into my neck. I'm going to have to use a different microphone for second hour. And so for hydrogen, this is the Rydberg constant. Now, other elements have a slightly different value for the same constant, and they have different n squareds, and for the Balmer series, H alpha, H beta, H gamma, H delta, the number inside the brackets is 2 squared and then n squared. Okay, so let's put in n equals 6. All right, and see how we can calculate the wavelength, okay? And we know what n equals 6 is. That's H delta. So it's going to be 410 nanometers. Let's figure it out. All right, so here we go, n equals 6. So there's the Balmer formula up there, 1 over lambda. And Thursday night I'll give you a little bit of a workout on Balmer series. You can calculate a couple. So you just plug in, 1 over 6 squared inside the square brackets. So that's 1 over 36. And then in the second level of this equation block, you have, when we haven't done anything with the Rydberg constant, that's still out in front, 1.097 times 10 to the 7 inverse meters. But the second line, I've converted to common denominators. Now, when you're doing this on homework or on the final exam, oh yes, you may find yourself doing this on the final exam. Convert to common denominators. All right, so 936 for 1/4, and then 1 over 36 for, 1 over 6 squared. Then subtract, so the third line is 8 over 36. And now you can calculate. Okay, so 8 times 1.097, EE7, divide by 36. And what you get is 2.438 EE6. But now remember, that's inverse meter, that's 1 over lambda. All right, that's not lambda. We want to flip-flop that to get lambda itself. Now, let me pause for questions. Make sure you guys don't get discombobulated here. Connor.
What's the last step you were saying? You got to flip that?
Yeah, because this is the formula for 1 over lambda. So if you want lambda itself, you got to calculate 2.438 and then hit the 1 over button on your calculator. Okay, question?
How do we know which elements, for hydrogen, how do we know what end to put?
The Rydberg constant has been measured. And basically, the formula, once you find the formula, you can figure out the value for capital R. So Balmer is probably the guy that figured that out. All right? It's something that you measure in the laboratory. Okay, so for us, that means it's going to be on the cover page of the exam. Okay. All right, so let's flip-flop that answer for lambda itself. Here we go. There's 1 over lambda, 2.438 times 10 to the 6 meters to the minus 1. All right, now flip-flop that. Ding. Now, meters to the minus 1 is now in the denominator. So, Jennifer, that means that my answer is going to have meters to the regular 1 in the numerator. And that's good because it's a wavelength. All right? So, there's your answer. So 2.438 EE6, and then hit the 1 over button, okay, which might be, on your calculator, it might be x to the minus 1, or it might be the 1 over x button. But anyway, so this is your answer in meters. Now, we want to get an answer in nanometers, all right? So we have to move the decimal point 9 spots over. And so just kind of bloop it over 9 spots, and you get 410.2 nanometers. Okay, and that's the deep violet H delta. And I believe there's another one, H epsilon. Very, very tough to see. Here's a professionally done photograph of the spectrum of hydrogen. H alpha, H beta, H gamma, H delta. And then you can see at the very far left, over here, you can see one more. That would be H epsilon. Okay, so the 6. And H alpha is like as common as dirt. So astronomers, when they're looking out at the universe and they put the starlight through a prism or through a diffraction grating. Oh, by the way, send your diffraction grating to the IL. Right now, pass your diffraction grating to the IL, please. Either left or right. Yeah, and don't touch it with your fingertips. All right, now you guys on the aisle, send the stacks forward. Send them, and don't. Or Steve, just come down the aisle and collect them. All right. All right. All right, Steve, and you could put them up on this desk up here. Connor.
So how did you know when you're moving the decimal place to the right when to stop?
Because the answer is in meters.
So, I mean, if it was up to
And
me, I'd stop at the 4 instead of 410.
yeah, that's right. That would be for scientific notation. Shh. But if you're just asking for the number of meters and scientific notation, then yeah, that's fine. But if you want to give a number of nanometers, then you got to go, 9 spaces over. So this is, as I've said before, Khalid, on a written test, this would be righteous. But for us, we have to enter our numbers with the clicker. So you might want to do, something. So if I ask for the whole number of nanometers, you'd type in 410, and then hit the send key. All right, and you'll have some of this on homework. You won't have a clicker question on it today, but for homework Thursday. Now, I cannot emphasize or overemphasize this idea here, that the regularity in the Balmer series, that pattern, there is a physical reason for that. It's not just, some willy-nilly, it's just. There is a physical reason for specific colors and no others. And that's what we're trying, and believe it or not, those specific colors and no others unlock the periodic table. Now, this is what the sun spectrum looks like. All right, and you can see there's a bunch of bullet holes in this spectrum. That's because at these different colors, like this, let me get my cursor over here. Okay, like right here, right above the word spectrum, there's a big gap. It's like somebody's got a tooth knocked out. That, I think, is actually H alpha being absorbed. So hydrogen will absorb H alpha. Any light that's at 656 nanometers, it'll absorb it. And anything at 410. 410 is probably up in here somewhere. All right. All those gaps that you see are from elements absorbing light of very specific colors. And you can see there, Connor, there's a zillion different elements that are showing their stripes, so to speak. All right. Now, here's a famous nebula out in the universe, the Rosette Nebula. And this is let me turn the lights off so you can see it. All right, as you can see it a little bit better. That's the Rosette Nebula in natural light, and it's mostly H alpha. It's reddish when we look at it. Now, you can't see it with the naked eye. You have to have a pretty good telescope. You have to have a pretty good camera. But it's reddish from H alpha. Now, here's what a false color image of the same nebula. And this is from the Astronomy Picture of the Day NASA website. In this one, sulfur they did a false color. They looked for the spectrum of sulfur. We did hydrogen helium, and neon, but you can do sulfur, you can do nitrogen, oxygen. Okay, and oxygen here is marked in green. And it's kind of hard to see here. Actually, the inner region is blue, really red. That's H alpha. So they false colored the H alpha, which to the naked eye is red. They false colored it blue here to show up the other colors, the other elements that are there. So when we look at the Rosette Nebula, we think to ourselves, oh my goodness, why is there an outer layer loaded with sulfur? And why is the hydrogen in the middle? And why is there a little bit of oxygen between the sulfur and the hydrogen? That's what astronomers and astrophysicists want to figure out. So let's talk about the quantum theory of the hydrogen atom. Here's another. This is a famous supernova remnant in the constellation Taurus. Very tough to see. But it's in red H alpha light. Let me bring the lights back up so you can take notes. So here's what we got. The hydrogen atom, it's a proton and an electron. Proton in red, electron in blue. The quantum theory is there's only a few orbital levels allowed. The electron only lives at certain specific altitudes, no others. Each altitude has a specific EPE. Because the EPE depends on R. It depends on the distance from the proton out to the electron. All right? Now, certain specific altitudes means certain specific potential energies. And they're countable. So here's the other thing, that those energy levels, there's a specific set and you can count them. From the lowest energy level, n equals 1, on out to 2, 3, 4, and on out. All right? So countable energy levels. Countable altitudes, countable energy levels. All right? And so you have your electron at, and let's say that we've got an electron at n equals 3. And when it drops down when it loses energy, it can only lose enough energy to get down to one of the lower levels, n equals 2 or n equals 1. It cannot go to n equals 2.7. If this were a gravitational system, we could put a satellite at any altitude we want pretty much. If we have a big enough rocket, good enough precision, we can, measure it out to the nearest centimeter if we want. But not with atoms. And so when the electron it dips from n equals 3 down to n equals 2, it emits a red H alpha photon. That's why the number 2 is squared in the denominator, and that's why n equals 3 corresponds to H alpha. Because the H alpha is a photon emitted with the leftover energy from n equals 3 down to n equals 2. Right? You lose potential energy as you drop down. Well, where does that energy go? It doesn't go into kinetic energy. It goes into the energy of the outgoing photon. So that's the basic idea for the quantum theory of hydrogen. The orbits are numbered and countable. The electron emits a photon of light when it drops to a lower energy level. And hey, you guys, when it absorbs a certain color of light, when it absorbs a 656 nanometer photon coming in, it jumps back up from n equals 2 back up to n equals 3. It can't go up to n equals 2.3 or 2.407 or anything like that. It can only go up to n equals 3 or maybe n equals 4, n equals 5, n equals 6. All right, and when it does that, it absorbs it because it absorbs a specific color. Now, the guys that figure this out are Niels Bohr, the guy in the front, and then the guy in the back there smoking his pipe or whatever is Albert Einstein. So they figured out, this is basically the Bohr model of the hydrogen atom, countable quantized atomic energy levels. And here's the kicker. From the color, they could figure out the frequency. From the size of the charge of the electron and the proton, they were able to figure out their energy. And guess what? It all obeyed this simple rule. The energy of the photon was Planck's constant times the frequency. And it all fitted perfectly for hydrogen. The one electron, they figured what that was about. One proton, they figured that out. And H, Planck's constant. Now we've got Planck's constant. The one constant to rule them all. So let's look at this formula, and let's make a note. Frequency is, and just make a note, frequency F calculated from wavelength. Wavelength measured in the laboratory with the diffraction grating and doing a little bit of trig. All right? So laboratory, you look at your H alpha, you measure, it's going to go through the diffraction grating and cut a little bit to the left or to the right. And you measure those angles, you do a little bit of trig, and you figure out lambda. So lambda is something that you can measure in the lab. Then you use the speed of light and figure out frequency. And then you know EPE, because you know Coulomb's constant and the charge on the proton and the electron. And it just so happens that when you calculate the energy and you calculate the frequency, it fits exactly into this formula. And this is why Planck's constant is the one constant that rules them all. And it is the key to understanding the periodic table. Now, let me cut back here. One more thing here. Let's go back to this little picture here. Electrons orbiting a nucleus. Periodic system. Periodic system. Phase portrait is an ellipse. And on Thursday, when we talk some more about Professor Planck, I'll tell you more about the phase portrait and de Broglie's relation. All right, you're dismissed. No homework tonight.